Okay, for FRKeynote 5, there is a common physics laboratory exercise shown where a person uses different masses to measure the restoring forces created by springs by hanging the spring vertically. The data of the experiment is shown below right here, and there's a picture of it too. So part A wants us to use the data provided to generate a graph that is associated with Hooke's law, and so it tells us to label our x and y axis and make sure it's to include SI units. Okay, so let's see. Wait, hold up. So here's our graph. So first I'm gonna make my graph. I know that the Hooke's law graph involves force and the distance compress or stretch. So, my y-axis is going to be F, and my x-axis is going to be x in terms of meters or the distance stretch. Okay, so let's see. 5. And this is F in terms of newtons. This is, by the way, the same as W right here, the weight of the masses. Here's my x-axis. This is the x position or the distance stretch, and it's in meters. So looking at my graph, it looks like I need increments of 0.05 or 0.025. So .12. Sorry, this is bad. Here, I just made it. Just making sure it's a little more stretched out. 0. Wait, this is 0.1. This is 0.125. Okay. So first point is all zeros. So 0 and 0. So right here. Right here. Second point, 0.9. Wait, no, 0.025 is my x. So right here, and my y is 0.98, so it's just below 1 a little bit. This is my second point. Third point is 0.05 for my x, and my y is 1.96, so just below 2. Right there. Third point or fourth point, 0.076, so slightly to the right of this, and 2.94, so just below 3. My next point is 0.099, and my y is 3.92, so just below 4 and just to the left of 0.1, so right about here. And my last point is just to the right of my last coordinate here, so 0.127, and 4.9 is my y, so just below 5. Should be right here. So looking at the data, it looks like it forms almost a linear line, which does support Hooke's law. So that's my graph. Okay. So part B asks us to determine if the experimental data follows Hooke's law. So looking at the graph, obviously it's yes, and the reason is because let's see, the experimental data does follow Hooke's law. Now, Hooke's law states that the force needed to stretch or compress a spring by some distance x, where some distance x scales linearly with respect to that distance. And the formula for this is essentially Fs is equal to Kx. So that is what Hooke's law states. So the graph does verify this. Verifies this by showing a linear relationship between F and X, the distance stretch. So it does verify Hooke's law, or it does follow Hooke's law. And this comes from the data, so the data does support Hooke's law. Okay, so part C asks us if a 0.8 kilogram mass is used, how far would it stretch? How far will this should be stretched? How far will it stretch the spring from its original resting position at x equals 0? Okay, so to do this, I first need to find my spring constant. So let's see, this is part C. To find my spring constant, I'm going to use this equation, of course, and I can use any point on the data to help me find my spring constant. Now, it looks to me that these three data right here form a straight line, and these just are a bit skewed. So I'm gonna use any of these three numbers up here from here. I'm gonna choose this middle one. So I'm gonna use 0.98 as my force of the spring, and that's going to be equal to K times X. X is 0.025 meters. That is the corresponding X. So solving for K, I divide this over, so K is going to be equal to 0.98 divided by, oh, this is newtons by the way, divided by 0.025, and my spring constant turns out to be 39.2 newtons per meter. Is my units. So that's my spring constant. Now I can use this to help me find how the spring was stretched if a 0.8 kilogram weight was used. Okay, so once again, my Fs, or my F, when it's fully stretched, my Fs, or my F of spring, is going to be equal to the weight of this weight of the object. So it's going to be equal to Fg. Fs is equal to Fg, so Fg is mg, and so my Fs is going to be equal to 0.8 kilograms times 9.8 meters per second squared. And so my Fs is 7.84 newtons. Okay, now I'm gonna plug it into the original. Now I'm gonna use this with the original equation, along with my k and my k to find how much distance is stretched. Okay, so my Fs is 7.84 newtons. My spring constant is 39.2 newtons per meters, and I want to find the distance stretched, which is x. So if I want to isolate for x, I just divide 39.2 over to this side, and so my x turns out to be 0.2 meters stretched from the original resting position. Okay. Hello, sorry, my phone died, so I had to get a charger real quick. Anyways, for part D, we are told to refer to the second data set, which is this one right here. And it tells us if the 0.1 mass is stretched, stretched, an additional length of 0.082 meters from its equilibrium position at x equals 0.025 meters, then release. Use conservation of energy and calculate the speed of the mass the instant it reaches the equilibrium position. Okay, so what I need to do first for part D is find the PE spring when it is stretched, the additional length of 0.082 meters. So PE spring is going to be equal to 1/2 times the constant times the distance stretch, delta x, and this squared. Okay, so in our case, this is PE when the spring has stretched a length of 0.082 meters. And so this is going to be equal to 1/2. Our constant we found to be 39.2 newtons per meter. And our distance stretch is 0.082 meters and square. And so we plug this in the calculator and we get 0.132 joules as our potential energy of the spring when the spring has stretched this much. Okay, so if the spring goes back to equilibrium, at the equilibrium point, all of PE spring will be converted to kinetic energy of the mass. And so this means PE when stretched a distance of 0.082 meters is going to be equal to the Ke at equilibrium. Now Ke at equilibrium is obviously 1/2 mv squared. And so now I'm just going to plug in my numbers. So we found our PE when stretched this is PE spring, by the way. PE when stretched at a distance of 0.082 meters, and that is 0.132 joules. Our KE is 1/2, mass is 0.1 kilograms, and velocity is what we're trying to find, so v squared. So I'm gonna multiply 2 and divide by 0.1 to this side, and that's gonna get me 2.636 on this side is equal to v squared on this side. Solving for v, I'm going to square root on this side, so v is equal to square root of 2.636, and that gets me 1.624 meters per second. Now it asks for speed, so what I have to do is basically just take the absolute value of velocity. It still remains positive, so this is my answer. 1.624 meters per second is my speed once the mass has returned to equilibrium. Okay, we're on part E now. Part E says if instead the mass is stretched an additional length of 0.164 meters, twice the previous length in part D, calculate the new speed at the equilibrium position and clearly state a relationship between the distance stretched and the maximum velocity at equilibrium position. Okay, so same deal. We're gonna have to first find PE spring once it is stretched the amount that we were told to stretch it. So PE spring again is 1/2 K times delta X squared, similar to up here. Now in our case, we are told to stretch the string or the spring a distance of 0.164 meters this time, so double of this. And that means that our PE spring is going to be equal to 1/2 times, so the constant is 39.2 newtons per meters, and our distance stretch is 0.164 meters, and then square. Plugging in this into the calculator, we're going to get 0.527 joules as our PE spring. This is PE spring, by the way. Oof. PE spring when stretched at a distance of 0.164 meters. Okay. So now the same deal again. My PE spring will be converted all to kinetic energy once it returns to the equilibrium position. So PE spring when stretched a distance of 0.164 meters, it's going to be equal, all converted to KE. PE spring we found right here, 0.527 joules. So I'm plugging that in. KE, the formula is 1/2 mv squared again, so 1/2, the mass is going to be 0.1 kilograms, and v is what we're trying to solve for, and this is v squared. So if we want to solve for v, we're going to multiply 2 over and divide by 0.1, so this side is going to turn to 10.543 is equal to v squared. Solving for v, I'm going to square root both sides. So v is equal to 10.5 square root of 10.543, and that's going to get me 3.242 meters per second. Now once again, it wants me to find speed, so of course absolute value, the velocity, is still positive, so it stays the same. So this is my speed when stretched at the equilibrium position when the spring was originally stretched a distance of 0.164 meters. Okay, now I have to address the relationship between distance, stretch, and the maximum velocity at the equilibrium position. Okay, so I'm gonna run through what we just did. So what we did was we showed that PE spring, it was gonna be converted to KE. So that means that 1/2 kx squared is gonna be equal to 1/2 mv squared. The 1/2s can cancel, and so I'm gonna isolate for v. So by isolating for v, I'm gonna divide m over. So kx squared divided by m is equal to v. Or it is v squared, and I square root everything. V is equal to the square root of kx squared divided by m. So, and then this is, this is a square root. I mean, this is a square in a square root, so I can take out the x. So, v is going to be equal to x square root of k and divided by m. Okay, so from this equation, I know that these two are constant, and this shows the relationship between v and x. It's a linear relationship, and from what I've seen based on the previous parts at D and E, as the distance stretch increases, the velocity at the equilibrium will also increase. So that is what I'm going to state the relationship as. So there is a linear relationship between distance stretched and maximum velocity at the equilibrium position. As x increases, as the distance of stretch increases, the velocity at the equilibrium position will also increase. Will increase proportionally, meaning linearly, proportionally to x. And same thing as it decreases. So as x decreases, as the distance stretch decreases, v will decrease proportionally to x. All right, there we go. That's the relationship.